All right, let's just get right into it. Welcome to this rapid review explainer for Chapter 8, designed to perfectly prepare you for your internal convection and fluid flow exam. Look, if you're a mechanical engineering student, you already know that internal convection is exactly where the math gets real, and those formulas start stacking up fast. So today, we're going to cut through the noise and turn all of that into a very practical, step-by-step guide.
Here is your step-by-step survival checklist for today. We'll be hitting 1. Laminar flow ground rules. 2. Constant flex versus surface temp. 3. The Nusselt number cheat sheet. 4. Non-circular tube geometry. 5. The thermal entrance region. And 6. Exam pitfalls involving evaluating properties.
Okay, Section 1. Laminar flow ground rules. The baseline assumptions. Before we can use any of the elegant math in this chapter, we've got to set our baseline rules.
Seriously, without these, our equations just completely fall apart. For our specific analysis of straight circular pipes to actually work on your exam, you must mentally check off these 4 mandatory conditions. Number 1, the flow has to be steady, meaning things aren't changing as time ticks by. Number 2, it must be laminar. Picture a really smooth, highly organized, layered flow. Definitely not the chaotic swirling you'd see in turbulent flow. Number 3, it needs to be incompressible, so the fluid density stays constant the whole way through. And finally, number 4, fully developed. This just means the velocity and temperature profiles have stabilized, and they aren't shifting around anymore as they move down the pipe. Definitely write this checklist down in your notes.
Moving right along to Section 2, constant flux versus surface temp, the core conflict.
Let's see how those baseline rules build into the 2 major heat transfer scenarios you've got to distinguish between. Most exam questions are going to explicitly state one of these 2 conditions, and you need to spot the difference instantly. On one hand, we have constant surface heat flux. This means the exact same amount of heat is being added or removed per unit area along the wall. A great real-world example of this would be an electric resistance heating tape, wrapped evenly all the way around a pipe. On the flip side, we have constant surface temperature, which means the pipe wall itself is held at a fixed, uniform temp. You'd see this in the real world if a pipe was running through a massive boiling water bath, or maybe a jacket of condensing steam. You really have to identify which system you're dealing with right out of the gate. Check out this sketch here showing the parabolic velocity profile. When you have fully developed laminar flow paired with a constant surface temperature, an amazing thing actually happens. The math simplifies. Both the friction factor and the heat transfer coefficient remain perfectly constant in this fully developed region. You can see from the arrows how the fluid in the exact center is moving the fastest, while the fluid right up against the walls just sort of sticks to it, which creates that beautiful parabolic curve. Section 3, the Nusselt number cheat sheet. Memorize these. So the crucial takeaway here is how this difference completely changes our Nusselt number. To use a super simple analogy, think of the Nusselt number as an efficiency constant, kind of like a performance multiplier. It tells us how much better our convective heat transfer is compared to if the fluid were just sitting there conducting heat while perfectly still. Here is the cheat sheet you need to memorize. When you identify a constant heat flux problem, boom, the Nusselt number is exactly 4.36. But if it's a constant surface temperature, that number drops to 3.66. Notice the gap there? The Nusselt number for constant heat flux is roughly 16% higher than our constant surface temperature baseline. Memorizing this will literally save you minutes of tedious calculation on an exam. I actually love how the textbook summarizes this phenomenon. It notes that in fully developed laminar flow with constant heat flux at the wall, the Nusselt number does not care about your flow speed, and it doesn't care about your fluid type. Just like a strictly enforced speed limit on a highway, it is always 4.36, simple and elegant. Whether you've got thick oil trickling through or water streaming smoothly, as long as it fits our ground rules, that 4.36 is locked in.
All right, Section 4, non-circular tube geometry, beyond the circle.
Now, what happens on the exam if your professor hands you a rectangular duct or maybe a triangular vent instead of a perfectly circular pipe? Well, obviously, you can't use a regular diameter. We have to adapt by using a clever little tool called the hydraulic diameter. Think of it as a universal adapter, a generalized diameter for literally any shape. And the formula is incredibly straightforward. It's just 4 times the cross-sectional area divided by the wetted perimeter. This brilliant equation lets us take all our analysis and extend it to non-circular tubes effortlessly. Once you calculate that hydraulic diameter, you're pretty much on easy street. You simply cross-reference it with a chart, like Table 8-1 shown here. You find your specific geometry, say a rectangle, an ellipse, maybe an isosceles triangle, check the ratio of its sides, and just pull out the exact constant Nusselt number and friction factor you need. It turns what looks like a really complex geometry problem right back into a simple lookup.
Section 5. The thermal entrance region. Journey of a fluid.
Now, let's zoom in a bit and follow a story. Let's trace the journey of a single fluid particle traveling into what I like to call the Wild West of the pipe, the thermal entrance region. Imagine our fluid just entering the pipe. Step 1, the fluid hits the walls and the thermal boundary layer immediately begins developing. Basically, the fluid temperature is frantically trying to adjust to the wall's temperature. Step 2, the fluid travels further down the length of the pipe. As it moves, these boundary layers from the top and bottom walls grow thicker and thicker, eventually merging right in the middle. Finally, step 3, all those chaotic entrance effects fade away, and the whole thing settles into that smooth, fully developed flow where our steady Nussel number of 3.66 takes over.
So let's do a quick active recall practice drill right now. Based on that story of the boundary layers growing and merging, where do you think the convective heat transfer is actually stronger? Is it in that initial entrance region or later on in the fully developed flow? If you guessed the entrance region, you nailed it. Because the thermal boundary layer is still extremely thin right when the fluid enters, the temperature gradient there is incredibly steep. This causes the average Nusselt number to spike massively near the entrance before it slowly drops back down to that steady 3.66. You absolutely must remember this distinction, especially when calculating heat transfer differences for very short pipes. And finally, Section 6, Exam Pitfalls, Evaluating Properties.
Listen up, because we've reached the final and, honestly, most dangerous part of our explainer, the common exam pitfalls where points are just instantly lost. We are talking about fluid property selection. You need to create a mental flowchart for how you select these properties based on temperature, because the split logic here trips up so many students. As a general rule, you must evaluate properties, like your thermal conductivity, for example, at the bulk mean fluid temperature. That's just the average of the inlet and outlet temperatures. Easy enough, right? But there is one major exception: viscosity.
Whatever you do, do not fall into the viscosity trap. Fluid viscosity, how thick or slick the fluid is, varies heavily with temperature. Just think of cold honey versus warm honey. Huge difference, right? Because the fluid right up against the wall is at a very different temperature than the fluid flowing in the middle, the viscosity right at the wall is totally different. So when your equation calls for surface viscosity, which is usually denoted with a little s subscript, it absolutely unconditionally must be evaluated at the surface temperature. If you use the bulk temperature for this, your whole calculation is going to be way off.
Well, there you have it. You now have the ultimate rapid review checklist. You know the 4 flow rules, the vital difference between flux and temperature, your Nusselt multipliers, how to use the hydraulic diameter adapter, why the entrance region spikes, and most importantly, you have the foresight to avoid that nasty viscosity trap. So, thinking about your upcoming exam, are you ready to competently master internal convection, or is there a blind spot you need to re-examine before test day? Keep this explainer handy as your ultimate review guide, and hey, happy studying!